Listen only mode.
My name is Chris Taylor. I'm a meteorologist who works at the Centre for Ecology and Hydrology in the UK. And I also lead the AMMA 2050 project, which is part of the Future Climate for Africa programme. And I'm going to share with you some work that we did, which was published in 2017 with a team of people from CEH and Leeds and Grenoble and other places in France, looking at climate change and how it may or may not be impacting intense rainfall in West Africa. So first of all, why should we be interested in climate change in West Africa? Well, the region experiences some very extreme variations in climate from year to year and decade to decade. And when we look at how we think climate will evolve in the future, our best estimates of climate change based on climate models often show quite a strong divergence in whether it's going to get wetter or drier. At the same time, the population is rather vulnerable to climate variability and climate change, and there's a very weak capacity for planning. So if you put those things together, it is perhaps not surprising that there isn't very much climate change knowledge used in decision making for the medium term. So I'll just flesh out one or two of those items now. The first slide shows the observed trends in seasonal rainfall in the Sahel since the 1950s, and you'll see that up until the 1970s, rainfall was pretty good actually, and then pretty strong, and then there was a drought period in the 70s and 80s, and sort of kind of ground to an end at the end of the 90s. And since then, we've had, on average, fairly intermediate rainfall, but still very strong variations from one year to the next. We don't really fully understand why this variation has occurred. We know that it's linked to global ocean temperatures, but we don't know the extent to which those ocean temperature variations are part of the natural variability of the climate system, or whether they're actually forced by anthropogenic emissions of greenhouse gases and also aerosols. When we look into the future at changes in precipitation, on the right-hand side there is a map from the IPCC report showing areas in blue where precipitation is expected to increase, and red where it's expected to decrease, and some grey areas. And the grey areas depict, so these maps are based on an ensemble of climate models, and where they're grey, that's suggesting that there is no clear consensus amongst the models as to whether the region is going to get wetter or drier. And if you look over at the end of the 20th century over West Africa, you'll see there's quite a lot of grey there, which means that we're not very confident about whether it's going to get wetter or drier. If we move over to Senegal, you can see that there's a little bit more confidence actually it's going to get drier there, and in further east that it's going to get wetter. But even in this area where we think there's some kind of reasonable confidence that more models than think it's going to get wetter than drier, it's actually quite hard to say with any confidence, give decision makers any steer as to how precipitation is going to evolve. So if you look over here on the left-hand side, each one of these dots is a climate model, and it's depicting a change in rainfall. So there's a model down there that's suggesting in this region of central and eastern Sahel, rainfall is going to decrease by 20%. That's the seasonal mean. Whereas there's a couple over here which are over 100%. So, what information is useful for decision makers? So as I've said, there's a lot of uncertainty in future projections of rainfall in the Sahel, and also to a somewhat lesser extent in temperature. The plot on the right-hand side is a very nice analysis that was done by Benjamin Sultan several years ago, which shows on the y-axis a change in rainfall in percent, and on the x-axis a change in temperature. And each of these little dots is a single climate model projection. So if we take one over here, for example, that single model is saying that the temperature is going to warm by about 4.5 degrees, and it's the rainfall in that instance is going to increase slightly. But the underlying colour, the shading there, indicates what that means for yield according to a simple crop model. And that suggests that the yields in that, for that particular region of climate space will decrease by 20 to 30%. And over on the left-hand side of this plot, there are individual years marked, and that illustrates the range of historical climate variability that farmers have experienced in recent decades. And you can see that even though they've experienced very extreme variations relative to the rest of the world, in fact, compared to what's coming in the future, it's really the projections are suggesting that we're going well beyond the observed, experienced range of climate variability. So, but notwithstanding that, this huge uncertainty, we can make adaptation decisions. For example, illustrated on the right-hand side, and that's what we're trying to do. And that's what the Future Climate for Africa programme is about. So another area which is very climate sensitive is flooding, and flooding in urban areas can have huge impacts on people and on infrastructure. For example, there was a flood event in September 2009 where 150,000 people in Ouagadougou had to leave their homes. And what we know from, well, this is analysis from a colleague of mine, Tazan Fawi at 2IE in Ouagadougou, based on looking at newspaper records, that the number of reported floods in Burkina Faso going from the 80s through to the present day has really gone up quite a lot. So you might think, well, some of that surely is to do with changes in land use, changes in urbanisation, perhaps also a change in the interest of newspapers in reporting floods. But also there's maybe a component to do with climate variability or climate change. So the challenge for us is to work out how we can use uncertain climate information to inform decision making, for example, in developing the city of Ouagadougou as it expands. So now just to say a few words about the AMMA 2050 project. AMMA came out of the African Monsoon Multidisciplinary Analysis, which has been a long-term series of projects, international projects, looking at West Africa. AMMA 2050 is a 15-member consortium. You'll see the logos down the side of the slide. And we're really interested in how the monsoon is going to change in future decades. So the monsoon is what brings the seasonal rainfall to West Africa. And whether we can use this information to support development and decision makers in this region. We've got a couple of pilot studies, one in Senegal and one in Ouagadougou, Burkina Faso. The latter looking at urban flood risk and the former looking at agriculture. And I would say that although we have this large area, in fact, quite a lot of the work that we're doing is in the Sahel. So this is this band stretching from Senegal out across to, well, we go about as far as Niger. Okay, so on to the more directly to the topic of the presentation, which is about thinking about intense rain and in the context of flood producing rain events and thinking about how they might change in the future. So what we do know is that a warmer atmosphere can hold more moisture. And this is, so for every degree of warming, you would expect that the atmosphere can hold up to 6 to 7% more moisture in the atmosphere. And that's known as the Clausius-Clapeyron relationship. So our first guess would be that as the climate warms, you would expect the intensity of the most extreme storms to scale with that temperature increase. So you'd expect it to go up by 6 to 7% per degree. And on the right-hand side, you can see a projection of the change in contribution of intense storms to total rainfall across the region. And the blues here indicate an increase of about 20 to 30% of the over this time by the end of the 21st century. And actually, I mean, current climate models tend to agree that intensities are going to rise, even though the different climate models some climate models may depict a decrease in overall seasonal rainfall. So, for example, this example shows the number of different climate models and the number of heavy rain days per season in Burkina Faso, I think. And there are some models over here which have got to show a decrease in the number of heavy rain days, but I think that's related to the fact that they're actually simulating a decrease in seasonal rainfall. So we just get fewer rain events. So we have to consider both of those things when we're thinking about future rainfall, future intense rain. But a key thing that we have to remember here is that current climate models are much less reliable in simulating intense rainfall than in other aspects of the climate system. So for climate models, we have more confidence in how they simulate temperature than in terms of how they simulate rainfall. And in particular, when we look at intense rain, they simply don't capture the processes within intense rainfall systems, particularly in tropical regions. Okay, so that's about models. So what do we know about Sahelian storms from observations? So the time series here is another version of the plot I showed earlier, showing the change in seasonal rainfall from the very wet 50s and 60s through to the 70s and 80s, and recovering somewhat since the late 1990s. But on the right-hand side, this shows the contribution of extreme rainfall to that seasonal total. What you'll see is that since the 70s and 80s, these storms have been getting more intense. So the intent of they're contributing more to the seasonal total. What we also know about intense rain in the Sahel is that, well, what we know about rain in the Sahel is that it's dominated by storm systems called mesoscale convective systems, which are powerful convective storms which travel hundreds of kilometers across the continent from east to west. And these are things which we can see rather easily from satellite. This is a sequence on the right-hand side from Meteosat, showing every half hour the temperature of the cloud tops associated with that flood event in Ouagadougou that I mentioned earlier. So Meteosat provides, since 1982, it provides us with sub-hourly cloud top temperatures. The cloud top temperature is interesting because it tells us about the height of the cloud, which in turn provides some indication about how intense the convection, the updrafts within the system are. But at the same time, the cloud top temperature is not telling us about rainfall, and certainly not telling us about extreme rainfall in a direct fashion. So what does extreme rainfall look like from Meteosat, from this cloud top temperature measure? So we did lots of analysis comparing those kinds of sequences of cloud areas, cold cloud areas, first with daily rain gauges from across the Sahel. And these showed us on the left-hand side that the larger the cloud area that you saw, the more likely you were to get extreme rainfall. And also, and so about 85% of extreme daily rainfall is associated with these big systems, which, when I say big, it means bigger than 25,000 kilometers square. And here we've used a temperature threshold to define what a cold cloud is minus 40 degrees. At the same time, we also know that the colder the cloud, on average, the more likely you are to get extreme rainfall. And that's very clear both from our comparisons with gauge data here and also with a more accurate snapshot of rainfall across a large region, which is from a spaceborne precipitation radar. So now we understand the relationship between something about the statistical relationship between extreme rainfall and the features that we can see. We can look back over the 35-year satellite record. And what we see on the right-hand side is the time series. This is for the June, July, August, September, which is the Sahel wet season. The time series of the typical number of systems that you will see if you look down at West Africa at 1800 in the evening. And you can see that it increases somewhat in the 1980s. It has lots of interannual variations. But actually, it turns out that that is very well correlated with the seasonal rainfall totals. So what that says to us is that the number of whether you get a good year of total rainfall or a bad year, you can approximate simply from looking at the number of these big systems that you see passing over your region. But if we look, so this was based on looking at MCS with a cold temperature. By cold, I mean colder than -40. If you start looking at much lower temperatures, which means much deeper cloud systems, you start to see something different. So on the down here, this is using a threshold of -70 degrees C. You start to see that actually this no longer looks like the interannual rainfall variability. It looks a lot more like a trend, a linear trend, and actually it's rather well correlated with global mean temperatures. So the observations I've been showing are based on operational satellites. There's been changes in technologies, changes in the quality, you know, sensors, drift, etc. So we were worried and needed to make sure that this wasn't just some kind of series of artifacts from the technology. So we checked this with a cross-calibrated data set using the same observations, but very carefully handled. And actually that confirmed that there is this very strong trend in the frequency of intense convective systems. And by intense, I mean using a threshold of -70. And that trend is equivalent to more than tripling since 1982. So it's a big deal. So what is why do we see this big change in cold, large systems? And it's primarily because the temperatures of the systems are getting colder. So that means the height of the systems they're getting higher, which is associated with more intense convection. And this plot down at the bottom just shows the time series of the temperature of MCS, and you can see at different times of day different signals, but they're all very clearly downward. And although there are uncertainties in the measurements of temperature, cloud top temperature, the trends that we see are much larger than any artifacts that we might get from the observation record. So where is this occurring? I've been showing you data from this blue box over here, but when we look across Africa as a whole, or North Africa during this June, July, August, September period, you'll see that, well, the shading shows where there is a strong trend, a significant trend, and the red colours indicate changes where basically it's increasing by about 80% per decade, so it's really rapid changes in the Northern Sahel. If you look elsewhere across the continent, across North Africa, there are areas which get quite a lot of MCS, over here, for example, in the Congo Basin, but we're not seeing a trend there. So this intensification trend during this season is really limited to the Sahel. So the question then is, well, is this limit? I mentioned earlier that it's well correlated with global mean temperatures. Is it actually, can we make any links with global warming? So what we did was look at the temperature trends across North Africa. And in the top left-hand plot, we've got observations which we carefully analysed, weeded out ones so that we were only looking at observations which had long, consistent records, and looked at the trend, and that's colour-coded. So blue means the temperatures have been going down over this 35-year record, and red means it's going up. And if you look in the Sahel, in fact, most of the colours are white or even a little bit blue, which means that there hasn't been, during the wet season, there hasn't been an increase in temperature over that period. Whereas over the rest of Africa, especially North Africa and in the desert, there's very strong temperature trends. And this is confirmed when we look at other data sources. Bear in mind that we're looking in a region where there aren't so many long-term measurements of weather and climate. So on the right-hand side, we use the ERA interim reanalysis product, which is a merging of observations and numerical models, a numerical model. And you see a similar picture with muted warming over the Sahel and warming elsewhere. Down here we have a measurement, a separate measurement again from satellite, which measures the temperature of the atmosphere in lowest 6 or 7 kilometers. So this was measuring the surface temperature. This is a much greater depth. And again, you see this pattern of warming over the Sahara, but actually over the Sahel, we're not seeing strong warming. And finally, on the right-hand side, this shows what the CMIP5 simulations think has happened in the historical period over the last 35 years. Well, over about 30 years over a similar period. So these models aren't capturing the real conditions of that were experienced during this period. They're an average over about 40 models, and they're capturing the response of the climate system to our increases in greenhouse gases and other constituents. And they show very clearly that there's a strong warming over North Africa, and particularly in the desert. So that's telling us that, and most of that is not natural variability, but it's linked to greenhouse gases. So what we can say is that the Sahel itself hasn't been warming during the wet season. So, you know, the first answer that I gave you about why you should get more intense rainfall, invoking the Clausius-Clapeyron equation, at least at a local scale, that can't explain the trend. So we would then, the next port of call, probably for a meteorologist, would be to think about, you know, whether, never mind the temperatures, whether humidity, how strong the humidity control is on the intensity of MCS. And what we found when we looked in the data was that we couldn't find a relationship between the intensity of MCS and atmospheric moisture over this 35-year record. So we looked instead at individual events, storm events, and again, we couldn't find any evidence that more intense storms were developing in a more humid atmosphere. So, so the figure in the middle here is an example of that. So this is based on measurements from about 400 storms, I think, at various sites across the Sahel, which would measure precipitable water, the amount of water vapor in the atmosphere. And they've all been composited such that the storm, these 400 storms, they all arrive at time zero. So if you look 18 hours ahead of that, the moisture is down here, and then it starts to rise, and it rises rather rapidly ahead of the storm in the 3 to 6 hours before the storm, and that's typical of these systems. So what we did was, when we stratified these storms into the most intense ones and the least intense ones, we found that the most intense ones were no moister 18 hours ahead, or even really 6 hours ahead, than the least intense storms. But what was different was that the most intense storms are associated with a much stronger increase in humidity in the atmosphere, actually at the time that the system is passing. So rather than thinking that increased moisture is driving more intense MCS, what we see in fact is that the most intense MCS are pulling moisture in from the surrounding area because of the very strong dynamics in the system. If it's not about moisture, you know, rising moisture in the atmosphere over this 35 years, then we need to think about alternative mechanisms. So we looked at correlations between all kinds of variables which we think are associated with the intensity of convection. And I'll talk you through these now. So on this plot here on temperature, this is a cross-section through the atmosphere, starting down near the ground and going up to 400 millibars, from the coast out well into the Sahara, with the Sahel sat in the middle. And the shading shows where there are correlations between temperature and our measure of intensity. And this red area indicates there's very significant correlations over here between the temperature in the Sahara, both at low levels, but also higher up, and the intensity of storms developing here. We also find a correlation at higher levels in the Sahel. We also find, when we look at the wind, how strong the wind is blowing from west to east or east to west, that we get more intense systems when there is stronger wind at low levels blowing from the west, coming in off the Atlantic Ocean, and also when the wind at about 4 or 5 kilometers up is stronger from the east. Now, these both are reinforcing existing wind patterns. So the contours here show the mean winds in this direction. And this negative here, this is known as the African easterly jet. It's a very important component of the whole West African monsoon. And what we're seeing is that the MCS are occurring when we've got a reinforced African easterly jet slightly to the north and reinforced westerlies at low levels. And the combination of those gives a stronger wind shear difference between these two levels, which we know is important for aspects of MCS. We also found, and I won't go into it, but we also found that there was more synoptic activity, so more weather systems, if you like, occurring associated with the years which had more intense storms. We also found that at mid-levels, about 600, 700 millibars over the Sahel, that we got more intense systems in years when it was rather dry there. So what we can say, and I'm happy to take questions on this, but these are all responses to, expected responses to Saharan warming. And they're all known to control the intensity of convection. I mean, there are various, bear in mind that there are many, theories about what controls the intensity of MCS, but these are all contenders in that, they're all respectable contenders. So, if we come back to our warming trends across Africa, I showed you earlier that there's no warming trend, or in fact slightly negative trend in some records in the Sahel, but also that the Sahara has been warming strongly. So that's true in all of these records. So we think that it's actually the temperature gradient rather than the temperature itself in the Sahel, which is important for this trend. And if you now look at the CMIP5 models, the ensembles, this is based on about 40 models, with the red line indicating the mean and the shading indicating the range from 1900 out to 2100. You can see that this temperature grade, the difference between the temperature at 10 and 20 degrees north, is projected to increase. It started increasing according to these models due to greenhouse forcing in the 1980s, and it's set to continue to increase in the future. And we expect this because I think there's a emerging understanding that the driest areas of the world, at least outside of in mid and low latitudes, the driest areas of the world are warming fastest under global warming. So we expect the deserts to warm more quickly. So that's a fairly reasonably robust projection that the Sahara is going to warm faster than the Sahel, and warm faster in turn than the Congo Basin, for example. So I'm just going to summarize those results by saying that we've seen a surprisingly strong increase in the frequency of these intense MCS in the last 35 years. This suggests a strong link with Saharan warming driven by anthropogenic emissions, and the climate models suggest that the Saharan warming is going to increase. So I just want to finish with a couple of slides about how this helps us with our problem in terms of thinking about decision makers, what it means in terms of climate science. So if we're thinking about future trends, what I emphasised at the beginning that in terms of seasonal rainfall, there can be quite a large disagreement between the climate models, even on the sign, let alone the magnitude of the change in seasonal rainfall in the Sahel. But one thing that the models do have consensus on is that the Sahara is going to warm more rapidly than the rest of the continent. So one of the things that we're interested in, if we believe, as we're homing in on the idea that the temperature gradient is an important aspect of controlling the intensity of convection, can we use the different depictions of the temperature gradient in the CMIP5 projections to get a better idea of what is most likely to occur? And secondly, we really want to better understand the relationship between convective intensity and the temperature gradient, and we're able to do that using a convection permitting model. So this is a very high spatial resolution model, which is really a step change in understanding how convective rainfall is going to change under climate change. This is being delivered by the Impala project, also funded under FCFA. And we can use this model unlike the CMIP5 models, does have a realistic depiction of controls on convective intensity. So, for example, it does include a nice representation of the sensitivity to wind shear. And then finally, for thinking about urban flooding and for agriculture, Well, the one thing that we can say right now is that conventional climate projections of the kind that I showed early on are likely to underestimate the trend. These models don't depict that there will have been a strong increase in rainfall intensity in the last 30 years. They're based, the physics is more closely associated with this Clausius-Clapeyron idea rather than other ideas that we've been exploring. If we think about agriculture, we'll expect with more intense rain, we'll expect more runoff, increased leaching of nutrient-poor soils in the Sahel. These MCS are associated with very strong winds, and so if they come at the time of year when crops are rather sensitive to winds, then there could be increased crop damage. And finally, if we just put aside for a moment the big uncertainties which still remain in the seasonal rainfall, if we have some confidence that intense storms are going to become more the norm, that implies that we get longer dry spells within the growing season. And that has implications for how crops develop. So with that, I'll end and take questions. Thank you.
Okay, thank you, Chris. At present, we haven't received any questions yet, but that I just wanted to alert those who are listening that on the right-hand side, you may see a little orange arrow. So if you click on that, you'll see a viewing panel where there will be a drop-down menu to question or chat. But probably if you could send something into the questions box, that would be very nice, and then I'll read them out for Chris to answer for you. I would also just remind you that this session has been recorded, and we will put it on the Future Climate for Africa website. We have one question which has just come in saying, why is the Sahel temperature not increasing?
Okay, so that's a good question. So what's happened in the last, as I mentioned earlier, during the wet season, the rainfall over this period, this 35 years period, has gone from a drought to improved rainfall conditions, which means that there's more moisture in the soil, which has allowed vegetation to become more robust and led to higher evaporation rates during the wet season. And that has helped to keep a lid, if you like, on the temperatures. If we hadn't had that recovery from the drought, then the temperatures probably would have gone up. They have certainly gone up prior to the wet season. So we've seen strong temperature increases in April, May, and June in the Sahel. So it's the soil moisture, if you like, buffers the warming trend.
Okay, we've got a few more.
Shall I come around so I can see?
No, well, yeah, sure. Says, oh gosh. Thanks, Chris. Can you talk a little bit about how you plan to use this information to better inform decision makers in urban areas or for agriculture?
Right. Well, that's the challenge for Future Climate for Africa. So we're trying to use this information to understand. First of all, we're looking at the processes which we think are important. We think we've identified the processes which are important in the historical period. We need to be sure that they're important in the future period. And we want to bring this information together. We need to bring this information together with what we know is robust, what we think is robust from climate change simulations, to create scenarios. I'm thinking about the flooding question. Think about realistic scenarios of flood events for the area of Ouagadougou. So we've developed a hydrological model which we can, for example, run with, let's say, the 1 in 5 year storm now, and we can use this information about the increasing intensification of storms to with these other sources of information to provide an indication of what plausible 5-year storms might look like in 2050 and simulate that storm in the impact of that storm in terms of flooding in Ouagadougou. And this is something that we're doing. We've got a meeting planned with the mayors of the Ouagadougou area in the next few months to kind of say where we've got to at this point and really hear from them as to exactly what we need to focus in on to get to the end of this chain. There's still some climate science to do, there's still some hydrological science to do, but there's an awful lot of translating that so that the decision makers can act on this information.
Okay, and there's another question that's coming in about the MCS formation. So if I understand this correctly, once we figure out the parameters for MCS formation and we figure out how to model trends, could we potentially also project for flood event risk, which is along the lines of what you were discussing just now to the previous question?
Yeah, I guess that's true. We need to understand how robust this relationship is between intense rainfall and the temperature gradient, and we need to understand the uncertainties in the temperature gradient. And we are also at the same time looking at the relationship between intense rainfall and flooding in Burkina Faso.
Yes, and we're mainly looking at also the Sahelian region, because there's a question coming in for coastal states. Mm-hmm. Marine spatial planning would be one of the solutions for also looking at flooding, is what someone is suggesting.
So,
but
yeah, it's not. We're not actually looking at. We've got a limited program. We didn't expect to find these results, I think it's fair to say, and we have focused the program on looking at what's happening in the Sahel. The more think about the Guinea coast, we may expect similar processes to be happening earlier in the season, earlier in the year, but we don't know, and that's not something which we have the resources to look at.
Yes, which interesting that you mentioned the Guinea coast, because we have another question that is referring to, do you think these results stand also for highlands of Guinea that supply much of the river flow to the Sahel?
That's a good question. It depends on the balance. In the Sahel, about 80 or 90% of the rainfall comes from MCS. That fraction decreases as you go further south. So it's about 40%, I think, or 50% when you get down to the south coast of West Africa. I think it will have implications for runoff generation in the Guinea Highlands, but also there's a lot of locally generated convective storms which may not have the same sensitivity to this temperature gradient that the long-lived MCS have.
Yes, so the Guinea coast is featuring in a number of questions because another person is asking, you said that the Sahara is influencing what is happening in the Sahel, and if I heard you correctly, if that is the case, what is the implication of the situation in the Sahel on the climate in the southern Western Africa, Gulf of Guinea coast?
That's a very good question, and it is, as I mentioned, temperatures in the Sahel before the wet season, so let's say March, April, May, have been rising. That means that the temperature gradient is increasing from south to north, which is influencing the easterly jet, which we think is important for MCS dynamics. So, but that's something that we're not, well, we'd like to look at, but we're unlikely to be able to look at in the current project because we've got so many other questions to answer.
Yes, so for the temperature in the Sahel, is this not increasing, and if not, why? Do you think?
So that sounds like a similar question. It's not increasing during the wet season on average, and that is because we're looking over 35 years. We're looking over 35 years, and the first 15 years of those 35 were drought years with very high temperatures. So it may be that if we computed trends from 2000 to, to now even, we would start to see a rise in temperature during the wet season. That's not something I've looked at, but certainly we would expect it to rise in the future, for sure. Temperatures in the wet season are going to rise in the future in the Sahel.
Okay, and I think we've time for two final questions. One is saying that you've touched on the possible implications for soil erosion, crop damage, etc. Are any projects working on this, i.e. implications for resource degradation currently? Do you know of other projects?
That's not, well, our partners at ISRA in Senegal are interested in soil fertility. They're not looking specifically at, I don't think specifically at the impact of soil erosion on that. But I know that there are other activities going on. I think Tanya's been involved in. Yes,
and also referring to the crop damage side, they are separate projects that are looking at that. Yeah. But our AMMA 2050 project is very much on the decadal scale that we're looking at things as well. So. Finally, we're sort of coming back again to the decision makers. With stakeholders in Senegal and Burkina Faso, it's recognized that climate change is now a reality that we need to cope with. In all the development strategies, you need to include climate change, specifically for areas which economy relies a lot on climate, rain-fed agriculture, river flows, fisheries, coastal tourism. Can we use uncertain climate information to advise on investment in agricultural and livestock?
So I'm not best placed to answer that question, but I would say from learning so much from my colleagues in AMMA 2050 in the past 2.5 years, I mean, one approach is just to look at scenarios, and I think this, in terms of intense rainfall, we would strongly favour the scenario that rainfall is going to continue to increase. It may be that the seasonal rainfall increases alongside that, in which case there will be a lot of flood events. It may be that the seasonal rainfall decreases, in which case we won't continue to see this really strong rise in flooding in Burkina Faso and other countries. But it's certainly a challenge, and I'm sure there are other people, people across the FCFA consortia who could talk for many hours, days about even trying to answer that question.
Yes, but it is something that we're all working towards, and projects like AMMA 2050 are building our knowledge and understanding. So we're getting there, but it just takes time and a collective effort. So. At which point I would like to say thank you very much to Chris for the presentation. Thank you to everybody for your participation and questions. We'll do our best to answer those that we've not been able to do in this time. And like we said, a recording will be available from the website. Please promote that and look at the survey and reply to that once it's sent after this webinar. So thank you very much, everybody.